Hi everyone, welcome to Introductory Python Tutorials with a special focus on image processing. In this video, let's perform the binary semantic segmentation using the UNet we have developed in the previous video. So if you haven't watched that, I definitely recommend you to watch it because we're going to use exactly the same UNet that we built using functions for encoder blocks and decoder blocks. Okay, in the last video, and then we are going to perform a binary semantic segmentation. So what do we mean by binary semantic segmentation? I think it's pretty clear, but if not, let's say you have an image on the left hand side. Here the object is to segment the mitochondria out of the background, out of this busy background. So this is binary because there are only two things I care about. One, background, and the other, mitochondria. I only want these two things to be separated. In fact, I only want the mitochondria to be separated. So a binary problem is actually a problem where you are focused on one single type of object. Binary gives the impression that, okay, you need two different things, but binary is basically you need one output. What is the probability that a pixel belongs to a pixel of mitochondria or it belongs to the background? That's it. So you need one output. If that output says 0.1, then I'll apply a threshold at 0.5 and say it's below 0.5, so it must be background. If it's above 0.5, it must be mitochondria. That's it. It's as simple. Okay, so that's what a binary semantic segmentation is. And again, we saw that this is how we can build a UNet. And all we're talking about here is, you see the output layer of con2D, you have one right there. This is the one output that we are actually getting right here. This is what a binary segmentation basically means. You have one output right there. Okay, and oh, sorry, I should have mentioned this one output. We are using sigmoid activation. And what is sigmoid? Again, go back to the video where I talked about it. But a quick explanation: this is a it goes between 0 to 1. Think of it as a probability. Using sigmoid function, you get a probability right there, and then you can set a threshold saying, hey, if the probability is below 0.5, I'm going to call it background. If it's above 0.5, this is again my mitochondria. Again, I know I'm repeating certain things, but these are very, very important when it comes to this topic right now. Okay, let's jump into the code and make this a bit fun right now. As usual, I'll share the code. So again, please focus on what I'm trying to do right here. So step number one, in Google Colab, you can do whatever I'm showing on your local computer. But if you have good GPU that's, with everything installed, great. Otherwise, try to use Colab because you don't have to worry about GPUs installing and all that. So first of all, change the runtime type. It's already GPU, so I'm good. And let me go ahead and connect. And it only allows you to work with one GPU at a time. You cannot run on multiple Colab accounts, with multiple GPUs. So be aware of that. And same with your local computer, right? If your GPU is already busy doing training a model, it's not like you can program it to do other tasks. Then your efficiency goes down. Pretty much similar. Okay, so now what data am I going to work with? This is the data here. Go ahead and click on this link. I'll share this, and it takes you to a page that looks like this. This is electron microscopy data set, and they have both the the original images and also the labels. And go ahead and download it. Download, each of these subvolumes, and I'm only working with the first one. And I took these images and masks, and I have cropped them into let's see, what am I doing here? Into size of 256 by 256. I actually cropped these images into 256 by 256. If you ask me how did I do that, I've been talking about patchify and unpatchify for a while, right? I mean, use the library called patchify that can actually generate patches out of your images, and then just write a couple of lines to save those images as JPEGs or TIFFs onto your local drive. If you want, you can code that. I mean, that's not difficult, right? I mean, you load a NumPy array of whatever size, and then you say I want to divide this into 256 by 256. So go ahead and get 256 at a time in X and Y, and then just save it to your drive. Don't forget to do exactly the same to your masks, so your input images and masks kind of match together. Obviously, you don't want a mismatch. Yeah. So I believe in this case I used patchify, and I said, okay, this is my large image. patchify it. So if my image is 512 by 512, then if I chop it into 256, then I'll get 2 by 2 by 256 by 256, right? I hope that makes sense. Okay, so 512 in X, 512 in Y, so it's 2 by 2. And I saved these four patches from my 512 by 512 onto my local drive. And then I did the same for my masks. So that's how I got my data set from here. Now that I have my 256 by 256, let's go ahead and start working. Okay, let's import the required libraries. I don't think I'm using normalize. Some of these you'll realize that I'm not using them, but they are left over from my earlier experiments. But I tend to leave them in case you want to use normalize in to scale your images. Yeah, so I'll just leave that. Okay, OS to walk through the files, OpenCV, Pillow to resize images if you have to, NumPy array obviously is what we are working with. PyPlot. I also left this min-max scaler if you want to use this to scale images instead of normalize. It's up to you. And from optimizers, I'm importing Atom, so we can use that as an optimizer. And I'm using Glob, so we can walk through the files. Okay, excuse me. Now I'm defining my image and mask directory. I have already, let me check, I have already connected my drive right there, Google Drive, and all I did is go to my data, wherever the data is, and then just get this copy path. Yeah, that's exactly what I've done. And this is the path to my images, this is the path to my masks. So this is just defining the directories. Next, I'll define the size and number of images I'd like to work with, because this, once I divide this, I think I ended up with about 1600 images. And then the training gets a bit slow. Of course, I recommend you to use all 1600 images. In my case, I just chose to use, 500 images or 1000. And I stopped at 1000 because I was getting decent results. So let's go ahead and, these are just variables, right? So now we need to define my image names. How do you define your image names? Well, first of all, why am I defining image names and not just loading the images from the disk? The problem is, this is again another important piece of advice before you spend a lot of time. When you load the images, just go ahead and load one after the other, like just write a for loop, yeah, and then load one after the other from a specific drive. The problem is on Windows it may work fine, because Windows probably organizes these based on the number or something. But on Linux, like definitely here, if you do that, it's probably your images are sorted based on the time it got added to the drive. Then when you load your images and your masks, they won't line up, because when you load the first image as 500 something, but first mask as 100 something, they don't line up. So we need to sort images based on the names or whatever criteria. We need to sort them, both images and masks, assuming your masks and images have similar names. Like if my image is image 121, my mask will be mask 121, right? That's the best way to do your images and masks. I hope this makes sense. So to sort my images, first let me get the names of the images and then I'll sort. Okay, so let's check out. First of all, glob.glob, it gets you the names, file names of what? Everything that has an extension of TIFF. So let's go ahead and load that and print the names. Let's go ahead and do that. So it's loading, it's reading all the files, getting the names, and just printing the names. I just want to show you how these names can be random. You see, my first image is 602.tiff. My next image, if I move right there, is 601.tiff, and then 600.tiff, all of a sudden 604.tiff. And if I go, it's not in an order, 648. If I go here, I have 1167, 1172, completely different, some random order. So I want these to be sorted. How do I do that? So I take my image names and I just do dot sort. Now let's go ahead and print it. And you see image 0, hopefully it should be image 1, image 2. After 1 it starts with 10 right there, and then it's 11, 100, 1000. It's sorting with, it's obviously looking at this 1 first, yeah? And then it goes to 2, I bet. So, and then 1002, 1003, 1004, so on, and then it jumps. So there is a specific order to this. That's it. That's all I'm trying to say. So of these images, I'm going to take only the first 1000 images. I have 1600 or something. So let me just take 1000 images. Again, why? Because I want my training to be a bit faster. This is optional. Okay. Once I do that, now is the time to read the images. So far, I have image names. I don't have images in the arrays. So the way I'm going to read, at this point, you can also use a data generator. So you read images in batches. We'll do a video on that in future. But for now, we are loading all 1000 images into the memory and then performing the training. Okay, how do we do that? This is for list comprehension. Like, for each image in these image name subset, right there, for each of these images, go ahead and do cv2.imread and each image, and then read that as a grayscale image. That's exactly what this line is doing. This will be very slow because now it's reading 1000 images. Okay, and while it's doing that, let's go ahead and look at the masks part. I'm doing exactly the same for masks. I'm reading all the mask names. You see glob.glob, and then I'm sorting them. And this step is very important if you want these images and masks to be sorted exactly the same way. So your images and masks will be lined up. Okay. Again, you'll lose your mind when things don't work out that way, and it takes forever to figure out exactly why. Okay, and then comes mask name 0 to 1000. That's what we have already done. And then comes cv2.imread. So these steps are identical to what I have done with my images, right? Except I just put everything in one block. So once the images are read, this will be a list, right? These are list of images. I convert them to NumPy array, and then I expand the dimensions so they're in the right format for my neural network. Okay, so that's what we are trying to do here. And same with my masks. And then I'm going to print out the shapes right here. So what I'll do is, again, I'm not sure how much longer this is going to take. So let me pause this video right now and continue as soon as we have the images ready. Well, it's been 3 to 4 minutes and this thing is still loading. So let's go ahead and stop it because I've already trained the model. So let me change this to 100 images so we can test the model, right? So let's go ahead and change that to 100 images. And now let's read these 100 images. And I hope this will be much faster than reading 1000 images. So hopefully it should be done in a few seconds, and we can continue because we need some images for testing. Okay, so I've already trained a model using 1000 images. Okay, so now let's convert those into NumPy arrays, because otherwise these images are just a list, right? So let's convert that and then expand the dimensions. Now let's do exactly the same for our masks, and this again should be pretty fast. There you go, reading these 100 masks. And anytime it should be done, and then we are back in business. Okay, so now let's go ahead and print out the shape of our images, masks, and what is the maximum pixel value in the image, and also the labels in the masks. Okay, we'll see why these are important. So let's print these. So we should have 100 images. Obviously we changed from 1000 to 100, so that's what that represents. Each image is 256 by 256 by 1, and that one is because it's a grayscale image. And we also have pretty much the same for masks. Now maximum pixel value is 255 in our images because we haven't normalized or scaled our input images. The labels in the mask are also 0 and 255. 0 corresponds to the background, which is the black background, and 255 corresponds to these bright images. That's exactly how they provided their data set. Nothing wrong with label 0 to 55. I like the labels to be 0, 1, 2, 3. So I'm going to divide this by 255, also divide this by 255, so we have scaling. Instead of dividing, you can also do min-max scalar or normalize, any of those things. So, but I chose the easy way. This works fine. Is divide my image dataset and mask dataset by 255. There you go. And now our values will be just 0 or 1 for my mask, and 0 to 1 for my images. So far, so good. Again, we haven't done much of anything. We just sorted our images and loaded the first 100 images in that sorted order, and same with our masks. And then we realized our images and masks need to be scaled, and then we just divided them by 255 to scale them. That's it. Now I'm dividing my images and masks into 80% for training, 20% for testing. Okay, so let's go ahead and do that, even though we're not going to train. The reason I'm doing that is it's always a good idea to perform a sanity check, meaning, hey, generate a random number between 0 to 100 in this case, or 99, and map out or plot your images and masks. See if they're lining up. That's exactly what I'm trying to do here. If they line up, I'm good to go, right? So that looks very good. That looks like the images and masks. Let's load another random image. Nothing there, great. Okay, so everything is matching up. This is very important to do because you're loading data from the disk, right? So, and then go ahead and define your model. We covered this in the last video, right? Defining the convolution block, defining the encoder block, which gives you these two, and a decoder block, and this is our model. Again, I don't want to waste your time by going through this because we spent half an hour talking about this in the last video. Okay, so we defined this model, and when I call it, it's going to return this model. So how do I call it? Well, where is it? Give it input shape and number of classes, right? And we also added these lines. So if my number of classes are not binary, then it's going to use softmax. If it is binary, meaning number of classes equals to 1, remember binary doesn't mean 2, binary means 1 output. Yeah, then it's going to use sigmoid. So my input dimensions or input shape is my image height, width, and number of channels, which is 256, 256, 1. So let's go ahead and define that and then build the model. Very simple. You provide this, and then we are going to compile the model by using Adam as our optimizer, binary cross entropy. This is a binary semantic segmentation. And metrics, we are going to use accuracy to train the metrics. Again, like I said, intersection over union is a better metric to track for semantic segmentation. We'll cover that in future, but accuracy works. It's not like it, but it just doesn't tell you how good it is, because here in my epoch 1 out of 25 epoch 1, yeah, this is my epoch 1 out of 50, I should say. How many epochs did I do? Sorry, I did 25 epochs, and these 50 are 50 iterations. So 1 out of 25. In the first epoch, the accuracy was bad for validation. In the second epoch, it's 92%. All of a sudden. But is that good or bad? We don't know, right? I mean, this is what the problem is with accuracy. So as I go down, I got 99% accuracy, but intersection over union will find out if it is good or bad. And then I saved my model. Okay, now let's go down, and this is how the plots look like. And let's go ahead and load the model. So we saved this under this name. So let's go ahead and load the model. I'm going to put compile equals to false because I'm not further training using this. I'm just using the model for inference. That's it. Okay. And for intersection over union calculation, I mean, you can track intersection over union, which is what you should do per every epoch. And that only happens if you put that intersection over union as part of your metrics that you're tracking here. But once it's done, you can calculate intersection over union over your entire data. That's what we are trying to do down here. First of all, we need to predict on our test data set. Yeah, so let's go ahead and predict. In our case, our test data set is only 20 images because we only are reading 100. I should have changed that, but let's check our model.predict. How do you predict? Model.predict. Again, this is same as in classification. It doesn't matter. It's always model.predict, and I'm predicting on my X test dataset. That's 20 images. And then I'm going to apply a threshold of 0.5, which means it converts every value probability, because when you do model.predict, it's going to give you sigmoid. I keep going back to the basics here, but again, these are very important. We are using activation function as sigmoid right here. A sigmoid gives you probability between 0 and 1, which means we have to convert that probability into class. And that's what we do with our threshold right there. Okay, so we are going to put every value, predicted value above 0.5. I'm going to call it mitochondria. That's what that is. So let's calculate intersection over union. The way you do that is go ahead and import mean IOU from keras.metrics and apply that. And this only works on TensorFlow 2 and later. Before that, you don't have that mean IOU, so it may throw some error. Okay, hopefully you're all working on TensorFlow 2 or later. So and for IOU calculations, I'm going to say my number of classes equals to 2 because I have 0 and 1. This may be confusing, but for Keras IOU, you have 2, 0 and 1. So it's going to look at, okay, you have 0 and 1. So let me calculate IOU. That's what this is doing. So you instantiate mean IOU right there with number of classes, and then you update the status of that using your predicted values from here. I'm going to use the thresholded and then the test values, right? So, and then go ahead and print the result. So previously with my, I don't know, 200 images, I got 91% IOU, which is excellent, by the way, I should say, mean IOU. 92% great. That means the intersection over union for this mitochondria and the background, we have 92%, for that. And anything above 90% for semantic segmentation, IOU is excellent. So let us set a threshold of 0.5 and do exactly this. Part of the code is basically loading an image, hopefully a random image. Yeah, right there. So loading a random image from our test data set and then predicting and printing. That's it, plotting. So let's do that. Not much to see here. Let's run it one more time. Hopefully we'll get a better image. Oh, God, we have all empty images. There you go. This is your testing label. This is what we got. The prediction. Isn't that amazing? Very good segmentation. Nothing there. We have many empty data sets. That is also not bad. Let's change this to X-train because we have more data in the train. And let's go ahead and check it. You can also load external image to check things out. Yeah. So there you go. That's, I mean, it's not perfect, but that's not bad. Segmentation. It is detecting mitochondria. I think, oh, I should have said X-train -1. Sorry. Okay, there you go. A little bit. It can be better. And one final time. Yeah, we already saw this. So I'm not sure why it's not looking at test number. But this is fine. X test. Let's change this to test before I share the code with you. Otherwise, you'll be wondering why I'm using train. Okay. I promise no more. Yeah. Let's end on this note. So what did we learn? Once you define your UNet, it's very easy. Everything else is data handling. You just divide your data into X-train, X-test, pass it to your UNet, let UNet do its magic, and then usually it works great. In the next video, let's look at multi-class, which is slightly different from binary because you have to convert your images to categorical. Other than that, everything else is the same. We are going to use exactly the same model. So you have one universal model no matter what you're working with. Okay, so again, let's meet again in the next video. Until then, do not forget to subscribe to this channel. Thank you, guys.